As a little application of the map theorem here, let's solve a problem from Putnam 1985. Specifically, I think, no, it wasn't exactly Putnam 85. It is a similar problem. You won't have any trouble solving the Putnam one once you've seen this one. So let n be a non-negative integer. Let bracket n be the set of the first n positive integers. Find the number of all triples A, B, C of subsets of n satisfying A intersect B intersect C is empty. So these aren't quite pairwise disjoint, but the intersection of all three is empty. So the Venn diagram can have overlaps between two, but there is nothing in the middle, so to speak. So how would we approach such a problem? It sounds reasonable to think about how can you choose A, after choosing A, how many ways you can choose B, and so on. This is not leading to a simple solution. Instead, let's try to use the bijection principle. So informally, here is how we proceed. So let us construct a triple ABC with this property. We do this as follows. First, we decide which of the three sets ABC will contain one. And by which we mean there can be several. It's not necessarily one. And in particular, there can be none. It's perfectly possible that one will not be in any of the three sets. The only thing that's not possible is that one will be in all three of them, because A intersect B intersect C is an empty set. Nothing can be common to all three of ABC. So how many choices do we have here? There is 2 to the 3 choices if you forget about this condition, because there is 2 choices depending on whether one will be in A or not, 2 more choices for whether one will be in B or not, and 2 choices about C. But we have to subtract 1 since 1 cannot belong to A, B, C at the same time. Next, we decide which of the sets will contain 2, and again, the same number of choices. And of course, 2 to the 3 minus 1 is 7, so we have 7 choices here. Then we do the same with the element 3. So we build the 3 sets element by element. We go over all the numbers, we go through all the numbers 1 to n, and we put each of them in 1 or 2 or none of the 3 sets ABC. So altogether, we thus make n choices. So we make choices n times, and each time there are 7 available choices. Thus, the total number of options is 7 to the n. So the number of all triples is 7 to the n. So you might find this a little bit imprecise. What does it mean to decide? What does it mean to construct? What are choices? So this argument can be formalized. I'm not going to do this later. I will not. You should not do this on a Putnam. You have better things to do. This would definitely work as a Putnam solution. But just if you're wondering how to make this rigorous, this is actually a bijection argument. Namely, the map that sends any triple to. So we built up a bijection from this set to this set. Once we have done this, the bijection principle tells us that the size of this is the size of this, and this is 7 to the n. How do we build it? we send ABC to the n tuple, where UI tells us which of the sets ABC the element I belongs to. So as we know from here, we have 7 choices, and what we need to do is to encode them as with numbers 1 up to 7. So for example, if I lies in none of the 3 sets, we give it the value 1. If I lies only in A, we give it the value 2. If I lies only in B, we give it the value 3. If I lies only in C, we give it the value 4, and so on. These are the options where it belongs to 2 sets. This is the last one. And finally, normally there would be an option for it to belong to all 3 sets, but because of this condition, this is not allowed. So we don't need 8 here. And this map is a bijection. So the bijection principle yields the result. But as I said, the bijection principle basically obscures the simple argument here. One thing that's important is that all of the choices are independent. Which of the sets ABC contain 1 has no effect on which of the sets can contain 3, for example, or 5 or 8. This is why this argument worked. If our choices here would restrict our choices here, we would have a problem with this argument. That would be a much more complicated problem. Fortunately, this condition is in a way entry by entry, so it doesn't really matter what we have chosen about 1 to all the following choices.